Yeah, I think that's what we're going to be doing. But what type of climate is the question? Think about it. I know. Why are sharpening your pencils? Okay, write your name. It's double-sided. So, but we're going to start on the back first. So, but you can write your name on either side. But we're not going to do it yet. I'm just going ahead and passing it out while y'all are sharpening your pencils. Okay, so I want you to turn and talk to your partner or anybody beside you or near you if you don't necessarily have somebody beside you. And I want you to discuss what you think a cocoa climate is, or what you think we're going to be doing today. Chocolate. Watching the Polar Express. We're not watching the Polar Express. So silly. You are. Okay, bring it back to me. And DeMarcus, share with me what you think a cocoa climate is going to be. It can be anything. There's no correct answer. Just shout something out to me. Like a bar graph? Okay. Well, actually, what is it, Izzy?
Exploring unequal heating relating to wind and ocean.
Okay, well, thank you for reading that to me. Beautiful. So today, we're going to be looking at what unequal heating and relating to wind currents looks like. So, what I want you to think about as I'm about to show you something is, what do you see happening to the whipped cream that I may be about to use? Why do you think it's moving without anyone stirring it? And does it stay at the top or does it mix into the cocoa? So, I'm about to show you. Can I get the out of the fridge?
Oh.
How many of you like whipped cream? Okay. Seth, what is something that you eat whipped cream on? Like hot cocoa? What about ice cream? Milkshakes? Okay, so. Alright, this requires complete silence and attention. Because it's hot and I'm about to walk around with it so that all of you can see. Now, I'm not putting much in mine because I want you guys. Yes, and you get to eat yours after. Okay, so there's nothing in this yet, right? It's just hot cocoa. So, but what if I, look at that steam.
That's cool. That's fine.
Can you see it having some condensation? Does it look like it's melting? Yeah?
Yes, it does.
But I'm not even swirling it around. It's just moving by itself, right? Yeah? But what if I swirl it around? Is it mixing together?
It's making
Okay, I want you to pass it around. You get to hold it, and I want you to give it one little stir. One little stir and pass. One little stir. But while you're doing that, does the whipped cream melt? Why do you think it's moving when I stir it, or why do you think it's moving when I don't stir it? And does it stay at the top, or does it mix into the cocoa? Is it mixing, or is it just sitting there? Because I think it's kind of mixing.
I'm sorry.
And then I want you to turn and talk to the people beside you and discuss your observations.
So I think it's.
What do you think this could symbolize? What do you think this could mean?
Okay, I think it is. I think
Oh, JW just brought up a good point. What does this kind of look like now? Have you ever seen chocolate? JW, go ahead and share.
Iceberg.
In the middle of summer.
An iceberg in Antarctica during the summer months.
So the ocean's dark.
Have you ever seen a penguin slide down an iceberg? Yeah.
In a movie one.
Have you ever seen the movies where a polar bear is jumping and the ice is breaking all around? That could be caused by what? What could cause that?
The fact of
Heat. Okay, so today we're going to think about it. This cup is a model of Earth's systems. The hot cocoa is like warm regions near the equator. Raise your hand if you know something, a place or a continent near the equator. Yes.
The Philippines.
Okay, where else?
Brazil.
Brazil. Now are those typically hotter areas or colder areas?
hot air.
Hotter.
Oh.
So the whipped cream is like cool air or water near the poles. Who knows what the North and South Pole are? Raise your hand if you know. If you've ever heard of the North or South Pole. Are they colder or hotter?
Colder.
When they meet, when air or water meets, movement happens, just like winds and ocean currents. So we're going to watch this video, and on your paper, you're going to be doing the Cocoa Climate Notes. It doesn't have to be anything extravagant, just anything that you see in the videos that respond to those questions. Yes. Because I want to do science with you. Why would you not want to do science? Well, you're going to do math with us as well.
Breathing in some fresh air.
Anything that you see that answer those questions, take
Have
a
you
little
ever
jot
jumped
note.
into a river and felt that the deeper, cooler water closer to your feet was moving faster than the shallow, warmer water at your knees? That's a current, which is the word we use to describe how water, or even air, flows within a larger body of water, or air. But what causes a current? Well, let's start with the sun. The sun actually heats Earth unevenly. We know that it's hotter near the equator and it gets colder as you go towards the poles. Near the equator, the sun's rays hit Earth's surface more directly, while near the poles, the sun's rays hit Earth's surface less directly. In both regions, the same amount of solar energy is hitting Earth, but near the equator, this energy is concentrated into a smaller area, and near the poles, it's spread out over a larger area. So the regions near the equator get more solar energy, which makes them warmer, and the regions near the poles get less solar energy, which makes them cooler. This uneven heating of Earth also affects air pressure. Where it's cooler near the poles, cool air will sink, making the air pressure high. But where it's warmer near the equator, warm air will rise, resulting in low pressure. This is where the terms low pressure cells and high pressure cells come from. The low pressure, warmer air at the equator rises into the upper atmosphere where it cools and flows away towards higher latitudes, away from the equator. Because the air is now cooler, it starts to sink again and creates a high pressure band near these latitudes. This process repeats and creates a pattern of high and low pressure bands from the equator to the poles. We know that air flows from areas of high pressure to areas of low pressure. This creates air currents, or winds. Now, you might think that these winds would blow in straight lines from high to low pressure areas, but the global wind patterns, which we call prevailing winds, look like they curve to the right in the northern hemisphere and to the left in the southern hemisphere. This curving has to do with the rotation of Earth and is called the Coriolis effect. As these prevailing winds blow across the surface of the land and water, they also push against the surface of the ocean and produce wind-driven surface currents, which help to move ocean water. Here's what the global pattern of ocean surface currents looks like. Like wind currents, ocean surface currents are also curved due to the Coriolis effect. We can see that in these currents that are traveling north and south, which curve to the right in the northern hemisphere and to the left in the southern hemisphere. Together, as these surface currents of the ocean connect, they form giant rotating systems of ocean currents called gyres. The currents that drive these gyres extend from the surface to about 1 kilometer down into the ocean and help to move water all around the globe. But these gyres aren't just moving water, they're moving heat energy as well. Water is pretty good at holding onto heat it absorbs from the sun. So, as the water in our oceans moves around the world through this gyre circulation, The water also carries heat. Here, warm water generally moves from the equator to the poles, and cold water moves from the poles to the equator. But the ocean has other deeper currents that are affected by differences in temperature and density. Remember how we talked about areas heated directly and less directly by the sun, and how that results in low and high pressure areas? Same thing with water, except that water density is affected by both temperature and salinity, which is a measure of how salty the ocean is. Cooler and saltier water is more dense, so it tends to sink, just like cool air. Whereas warmer and less salty water is less dense and tends to rise, just like warm air. So with these deeper ocean currents, water actually moves vertically or up and down. For example, water near the poles gets very cold. It also gets very salty because when sea ice is formed, the salt can't go into the ice. Instead, the salt stays behind in the water, and so the water gets saltier or more saline. Together, the coldness and salinity makes the water very dense, causing it to sink deep into the ocean. In other parts of the ocean, wind drags deep water up to the surface in a process called upwelling. These vertical currents are connected by horizontal currents at the surface and in the deep ocean. Collectively, this system of currents is known as the overturning circulation. You might also hear it called the global ocean conveyor belt. So here's a map showing the overturning circulation. This map might look a little bit strange, but here we're looking at Earth from the South Pole. So Australia and the southern tips of Africa and South America are closest to the center of the map, while Europe, most of Asia, and North America are at the edges. Now, if you follow the currents in the overturning circulation, you can see that they flow all over the world's oceans, from the Southern Ocean around the South Pole to the Pacific, the Indian, and all the way into the North Atlantic. Like the currents in the gyre circulation, the currents in the overturning circulation also carry and disperse heat energy all around the world. Here I am, back in my favorite river, wading around and enjoying currents of cool water flowing around my feet. And even though this river is small, the currents that flow through it are similar to the global wind and ocean currents that flow all around the world. So these currents connect in our atmosphere and oceans, which means that we are all connected. So currents connect us all around the world.
Okay, so I want you to discuss with the person beside you what is something that you found interesting about what we just discussed. Think about what JW said about the icebergs. Think about currents. Think about the hot chocolate. What you're about to do. Bring it back in 3, 2, 1. Ellie Boy, what is something that you learned from that video, or you found interesting, or you think may relate to our experiment today? Yeah, water carries heat. How many of you knew that water carries heat? Okay, I didn't know that. That was interesting to me when I was planning this. Will, what's something?
Okay. Some rays hit Earth unevenly, causing unequal heating around the world.
So does that kind of make sense why when you go to the beach, there's not icebergs in the middle of the ocean?
Yes.
But there are, where, in Antarctica? Yeah. Okay, so before we get started, we're going to accurately compose a ratio of cocoa to cream while writing it in your fraction and percent form. You're going to get to build a model representing how unequal heating of the Earth's surface caused movement in air and water. And then at the end, the easiest part is you're just going to use one of these vocabulary words that I'm about to show you. There's only 4, and they're pretty easy. To write your reflection of the results that you analyzed about the model that you are about to create. So our 4 vocabulary words, yes, Will. Yes, you may. Our 4 vocabulary words are poles. Everybody say poles.
Poles.
So poles are the 2 coldest areas on Earth, the North Pole and the South Pole, and they're where the sunlight hits the least. Does that make sense why it's kind of like the coldest? So the poles are much colder than the equator because they get less direct sunlight. Then we have Convection. How many of you have ever heard of convection? What is convection? Do you want to read it? Read what convection is.
Convection is the movement of warm air or water rising in cool air or water sinking.
Perfect. So convection in Earth's atmosphere helps move warm air upward and cool air downward, which affects our weather. Then we have a current. And current and convection are related because a current is a steady flow or movement of air or water in a certain direction. And then energy transfer, how many of you have a lot of energy all the time? Or how many of you feel like you have no energy? I have energy all the day, every day. So energy transfer is when heat moves from a warmer place to a cooler place. So we're about to discover what to do. So step one, I'm going to put you into groups and then we're going to go through the steps together. You're going to measure your cocoa. You're going to have a materials manager. Your materials manager is going to come get the cup and we're going to measure the cocoa. You're going to have a recorder in your group. In your group, the recorder is going to be working on filling out this chart with your group. What the chart is your ratio of your cocoa to cream in fraction form, percent form, and the observed speed, which I'll go over the observed speed later. And then you're going to have an observer, somebody that's real, all of you are watching, but somebody that's really watching, almost like the detective of the group. And then, depending on how many are in your group, you're going to have somebody that is kind of moving the cup, more of a stirrer. So I'm just going to count you off into groups. It doesn't matter what group you get in because every group is doing something. So I'm just going to count you off in numbers. We're going to have ones over there, twos right there, threes in the middle, fours right here, and fives kind of over here. So whatever number you get, you can go ahead and move to that area. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, Ellie Boy 3, 4, 5. Right here. 1, 2, 3, 4, 5. Fives are right there. 1s, 2s, 3s, 4s, 5s. And then you can go ahead and sit in desks that are near that area. Go ahead and sit in a desk near that area. Because you're going to need to write.
This is for you.
Twos are right over there, so sit where any of them usually sit. Sit in those desks right there. Threes are here. So Ellie Boy, you come right here. Okay, and then once you see who's in your group, go ahead and pick somebody to be the materials manager.
I at least have lavender.
I'll just be
And then once you have your materials manager picked, that manager needs to come see me.
I'll just
Okay. Your ratio is going to well, that's not
Yours over there.
yours is going to
No, not you.
and then you're going to get 4.
Jot down everything.
Now go observe.
What if we got a ratio?
What group are you with? Okay, 4 is going to
I thought we were getting that. Okay. Guess we're gonna have each other's DNA.
y'all are that drink some.
That would be so dumb.
And you're on 2. It's hot.
But nobody. But nobody needs nobody. So you have like drinks. But nobody needs nobody.
What do you mean group ratio? It means out of the people that
So you would just go
And then you're going to get 3 minutes. Oh, wait. 3 minutes.
Wait, and then 50. What are you doing?
And then
It's just group ratio. 4 out of I'm not going to that's what it means.
bye-bye. Observe. Alright, what's your group? You're going to get 4.5.
Out of 20 people. Fraction form? Okay, so times 5.
And 1 is 8. And then what group are you? So you're going to
So like, who's stirring?
It's a ratio.
Bye-bye.
Okay, that's good.
Okay, your ratio is cream to cocoa. Cream to cocoa. You should be observing. Somebody should be swirling it.
How am I supposed to
You need to, and when you swirl it, you need to model the earth. The earth doesn't zoom. The earth just kind of rotates. And I'm starting your ratio. What numbers did I tell you?
Okay, 2 and 2. I literally have no idea.
2 and 2.
I said what group? So you got 3 and 3.
That's a full, that's like, what are we measuring in like?
Your ratio? Okay, a good question. Step 1, we measured the cocoa and cream according to your ratio. If you don't remember what a ratio compares quantities to show how they relate. It's A to B, or it's A colon B. So your ratio is cream to cocoa. So how much cream that your materials manager got versus how much cocoa your materials manager got. You should be having somebody swirl. You should be observing. There's a reason why some people's are already gone and some people aren't. Not everybody got the same ratio.
It's 3 of them.
Okay. And then if y'all perform the experiment well enough, then you'll all get your own cup of hot chocolate. So you better be performing the experiment tonight. No. Y'all disintegrate.
It's 3 over 1. It's 3
And then I want you to be discussing with your group. I want you to be discussing and answer the questions on your paper for your cocoa climate reflection. What do you think this could be modeling? What is the point of this? Why did yours melt faster than somebody else's? Yes. It meant observed speed, but we're not really going to. Just like did it melt fast, did it melt slow? Did it melt accurately, like an average? Okay, I'll leave away. It is. Okay, y'all gonna have about 1 more minute. 1 more minute. You don't have to finish all of it.
But I'm like, bro, I got 639. I'm really good.
The observed speed did yours smell like average? Like, have you ever had much average? I feel like y'all need to writing this slow. Yeah. So about 30 more seconds. If you don't finish all the questions, that's okay. We're discussing them as a group. So like some of the questions, For example, the one that you just read, what number is that? Okay, like number 2, the first number 2, because I had a typo. The first number 2. How did the ratio of cocoa and cream affect the movement? Did you have more cream in yours than cocoa? Did you have less cream than other people? Describe that. How could that relate to heat change, etc., etc.? Okay, we're going to go ahead and discuss. So, you're going to log your results of your group on here. You do not have to worry about the speed, the observed speed. That was just something fun to see if you could tell how fast or slow it went. But you're going, in your group, you're going to write your ratio that you recorded. Somebody's going to write the fraction and the percent of that. And we're going to compare them. How many of you remember working on, when are we comparing ratios? How many of you remember what it's called? A rate. We're looking at the rate. That's something changed. Okay, group 1, you can go ahead and come write yours. And you only need one person to come up. So, one person from every group come up and write theirs.
It was way too fast. We couldn't even put the number on here fast enough.
Okay. Or did y'all
First
have
number
to?
down, it
Y'all had to. Okay. If your group has already come to write, then you should be silently answering the rest of your questions. You should be reflecting on what you just saw. Did you see steam? Did you see what's 50 or it's 50 per side? But we're gonna go. So you can just write. Just write.
Okay, so I have those. So I'm just gonna tableau. So the cream represents ice for number 2.
Okay, you're silently answering your questions.
How come there's 2 twos?
This is once your group is done, you can go back to your seat or go back to your
The cream represents ice.
Well, how about you write about it? Yeah, instead of laughing. Thank you. Okay, so I want you to look up on the board and we're going to discuss our results because I have the exact ratios that you should have had and the results of them. So group 1, what was your ratio?
4.
Okay.
4.
Or it could have been what? 4 to 2. So group 1 actually had 4 tablespoons of cream. To 2 tablespoons of cocoa. But you can still get that same result, so it doesn't even matter. Yes, I'm sure, I promise. Okay, so did yours melt on average or did yours melt slower or faster? Faster? Why did it melt faster?
because I shaped it a little more than normal.
Okay,
When we were doing this, it wasn't working, so we had to kind of do that.
so you did that.
Yeah.
Now, on Earth, Sometimes do things happen like earthquakes? Does that cause extra movement on Earth?
Yes.
So the Earth is always rotating, right? So the Earth is always moving, which means currents can always move, correct? Yeah. But sometimes we have natural disasters that cause a shift in Earth. Okay, group 2, what was your ratio? Okay, now that means that you had what? You had how many tablespoons of cream? And you had how many tablespoons of cocoa? Okay, now did yours melt pretty average, slow, or fast? Average. Now, are you spinning yours a lot or no? Okay, so JW said that he spun his what? Fast, but y'all's group said y'all spun it what? Average, kind of slow. So do you think that the movement of Earth can have an impact on our currents? Obviously, Earth is never going to spin any slower or faster, but can things on Earth impact our currents? Yeah. Okay, group 3, what was your ratio? 3 to 3. Now, when we have a ratio like that, doesn't it mean that it's kind of what? Equal? It's equal parts. You have 3 parts cream, 3 parts cocoa, right? Do you think that's the perfect balance in our experiment? It didn't take too long for what? Your cream to melt, but it also didn't go super fast or slow, right? So on Earth, do you think that we have a 3 to 3 ratio with our currents? No? Why not? Why don't we have an equal amount of currents? Like if our Earth was moving, do you think that the speed that our Earth moves is equal to how currents work? It's a balance, right? Yes, it's a balance. It's a balance. Okay, group 4, what was your ratio? What was your ratio?
From what I saw there, I had to change it. Originally, we got something different, but unfortunately, not true.
Okay. And did yours melt fast or slow? Kind of fast? Okay. And group 5, what was your ratio?
4.5. 4.5. It's a ratio. Oh.
4.5 to.
1.5.
Okay. And did yours have more cream in it or more cocoa?
More cocoa.
Yeah. So did yours melt fast or slow? Because you had less cream, right? And the cream represents what in this model? Icebergs. It represents cold winds, cold currents, and what does the cocoa represent? Yeah, warm water, warm wind, warm currents. Okay, moving on. Okay, so basically what this represents is the more heat energy, the more movement. For example, in the groups that had more ratios with higher cocoa amounts, you're going to have more movement. The movement is the whipped cream melting in your hot cocoa. So just like how the equator receives more sunlight and drives stronger ocean currents, the cooler regions near the poles move less, creating convection loops that help distribute heat across the planet. So how many of you know anything about the water cycle? Okay, and does the sun make evaporation happen?
Yes.
And through what type of energy? Solar. And what is about the sun it's known for? It's hot. Okay, that heat absorbs the energy in the water. Just like when you go to the ocean water is absorbed. It's heated because the shallower the water is, the faster and warmer it gets, right? Because it has less to heat and less currents to move around. Okay. So what about our model? In our model, what represents the warm areas of Earth like near the equator? We just discussed this. What does your cocoa represent? Yes. Correct. What does the whipped cream represent? The icebergs. Or what is so popular about icebergs? They're what? Cold. So the whipped cream represents the cool movement. So how does the movement of the cream and cocoa model how air and water move around our planet? So how does that model how it moves around our planet? Whoever knows this and thinks that they get it right can be the first to get the hot cocoa. The question is, how does the movement of the cream and cocoa model how your hot cocoa melted your whipped cream, and how does that model air and water moving around our planet? Yes.
It models the uneven heating of the plant because of the different amounts of cream and the different amounts of cocoa, because if they have a bunch of cream or a bunch of cocoa, and they would affect it.
Correct. So what ratio do you think represents more near the equator? One that has a lot more cocoa or one that has a lot more cream? Correct, because cocoa is warmer, right? And around the equator, it's warmer. So what would happen to Earth's weather if all areas received the same amount of heat?
It would be like the same temperature everywhere, and like the poles, like they wouldn't be called the poles anymore.
Right.
Everything would be the same.
Would we have more movement or no? Because what did this slide say? The more heat energy, the more movement. So would we have more movement if everywhere was the same? We wouldn't. Because we wouldn't have different variations of heat, right? And last but not least, so what was the point of this? Ocean currents move heat energy around Earth. Warm water near the equator rises and moves toward the poles, where cold water near the poles sink and move toward the equator. This continuous movement is caused by what? Unequal heating, keeping Earth's temperature more balanced. So your cocoa climate model connection, your hot cocoa model is a mini version of Earth's convection system. The hot cocoa represents warm ocean water near the equator. The cold whipped cream represents cold water or air near the poles. And when the two meet, the cream moves, swirls, and sinks just like cold, dense water in the ocean. The movement you observe in your cup models how heat energy moves through ocean currents, distributing warmth around the planet, which is why your whipped cream melted, because the heat moved around in the whipped cream, causing it to go into your cocoa. And the end. Great job.